the finite subcover that has to exist for that open cover, which again we're assuming X is compact. So. All right. Let's see here. Lemma 6.3 tells us that if we have S a compact subset of a Hausdorff space S compact subset of Hausdorff X, then for each X in the complement of X by S, there exist disjoint open neighborhoods of neighborhoods U of X and V of S. Let me see if I can draw a picture of that. So I'll use the plane because why not? Okay. So if I've got a compact subspace, like here's S, compact, right, closed and bounded. In the metric sense, that's what that means. And if I have X outside, I mean, okay, well, this is not a very exciting theorem in some sense. So X is out here, right? Out there. Disjoint open sets, so there's a U around X and V around S that what does that say? Isn't that, what's that? Wasn't that one of our T's? Oh, but the T3 assumed closed subset. This is compact subset. So in a Hausdorff space, a compact subset is behaving like a closed subset in a T3 space. It's another way to say this lemma. But I think the main purpose is what it's about to be used in. What's that? Yeah, that's the corollary. Corollary. A compact, thanks gang, compact subset. Is that immediately obvious from what I just wrote? Oh, actually, if you look at what the previous thing, that means that every point in the complement of the space by S has what property? It has the property that there is a open subset around it, right? Disjoint from V and thus from S. What does that mean? If you so think about this. If you take the union of all such possible U, like think about X varying over the complement, right? if you take the union of all such open sets U, right, they never hit S, and they hit every point in the complement. But they're also the union of open sets, which is open. Therefore, the complement of S is open, which means that S is, by definition, a closed set. And there you go. That's why this lemma implies compact means closed. There's more. Theorem Theorem 6.5. Compact Hausdorff space is normal. In other words, T2 implies T4 in the presence of compactness. So if you want to distinguish between the T3 versus T4 versus T2, you're going to have a really hard time if you try to use Hausdorff examples to see the distinction. Which is part of the struggle early on, because most people think about examples that are Hausdorff predominantly, especially in the applications of topology to analysis. By and large, we're interested in things that are Hausdorff. It's so important that when you study manifold theory, we assume that manifolds are a Hausdorff. I think Hausdorff T2 space is like the base topological assumption for most people beginning to talk about what's a manifold. So, all right, anyway, this theorem I actually should work out in detail. Theorem 6.6. And it says that the continuous image of a compact set is compact. F going from X to Y, then X compact, continuous, of course. Continuous are the only kind of functions that exist to us in topology. All right. Then X compact implies that F of X compact in Y, of course using the relative definition of compactness of a subspace. The proof is actually very easy. All right. So what we do is he says let, union over alpha. Alpha is in some index set lambda. The family of open sets covering the range f of x. Then, if we look at the inverse image of these guys, what's that give us? I mean, the way the function's defined. Oh, yes, those are exactly. For one thing, those are also open. But also, this has to hit all. I mean, if that covers the range, that has to also cover X. Like this is an open cover. It's an open cover of X. Yes, it's open because F is continuous, right? Why does it have to cover X, though? fun set theory reminder, courtesy of King. You said that the inverse image of a union is the union, and that's true for any kind of union, be it finite or infinite, right? Right. Should be a subset maybe, but so why is that X? Oh, because this, you're saying this is all of f of X. Is that what you're saying? That, I don't know about that. I do think, logically speaking, that should be open in the relative sense. Yeah, I think that should be. I mean, that's what I'm assuming. That should be f of x, right? So we're saying if the u alpha were just open in y, if they weren't. So what's going on here, guys? Is I don't know. Maybe this is the image. And so what we're fussing over at the moment is when I say family of open sets, do I mean, that cover f? Do I mean like this kind of? Right? See, I don't think I do. The family, it has to be anyway. All that matters to the question of whether or not f of x is compact in y is the intersection of those with. I mean, I have to consider open coverings of the range, so I can erase those and just think about I should just think about an open cover of the range. The thing is, anything outside of the range, right? Anything out here, right? If I look at the inverse image of the singleton containing y, we know what that is. I mean, it's the empty set. So there's u alpha. Have I said something wrong? Okay. Uh-huh. It is right. It would not be in. It wouldn't even necessarily be open in Y, much less a cover of it. Right. Yeah. Could be repaired. I mean, everything open in the range is the intersection of the range with an open set. So I could, like we were doing in the other argument, go back. But okay, let me get to it. So then what are we looking at? So, okay, so then this is an open cover of X, but X is what? Compact, therefore there exists a finite subcover, right? So we can find, finite subcover of X, and just take the image of that cover of X, and it gives you a finite subcover of your original, of this one. So if I call this thing, I don't know. So F of, well, the same. I mean, this is stupid. And I don't know why I'm making such a big deal out of it. Then U1 UI I equals 1 to da 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 n is finite subcover of f of x. Sorry, the proof is really quite beautiful. I'm sorry, I seem to have found a way to make it less beautiful, but my apologies. Ah, right. Yeah, this says that okay, so then the image is compact, right? But that doesn't say anything about all of y. If f is a what? If f is a surjection, then we get that y is compact. So, and there you go. That shows you the homeomorphism preserves compactness, because of course the bijection is a surjection. Yeah. So next up, see here, theorem 6.7. He says f continuous, so going from x to y, and so here x is compact, y is Hausdorff. So make these are our terms and conditions. And f is continuous. Like I said, if I forget to say it, if I talk about a function, I'm assuming it's continuous. If you find me a theorem in this book somewhere about a discontinuous function, let me know. I don't think there is one. I should never challenge math majors in that way. You'll find a way to make it true. If f is 1 to 1, then f is a homeomorphism. If f is 1 to 1, then f is a homeomorphism of x and its image. So the main point here is the data which is given. This is like the topological analog of, remember that theorem we have in linear algebra, that if you have a linear function, all right, and it's invertible, then the inverse is automatically linear. This is kind of the analog of this, because the content of this is, so we're assuming continuity of the original function, all right? And if it's 1 to 1, a function which is 1 to 1 is can automatically be viewed as the inverse function onto its image. Like, just throw away the codomain points you don't map to. It becomes a bijection, just from the set theory, right? If we have 1 to 1, it automatically is onto this, which means that we can view the f of x to f of x as a bijection. So this is saying that if x is compact and y is Hausdorff, then continuity of the original map automatically implies continuity of the inverse map. It's the topological analog of that theorem we have in linear, that linearity of the forward function automatically implies linearity of the inverse if it exists.
You said last time that if F maps open sets to open sets, that's called open map.
Yep.
So this is saying that if these conditions are met, then continuous implies open.
Yeah, and so continuous implies open. That's not usually the case. I think open is equivalent to continuity of the inverse if it exists. I mean, the data which is given here means the inverse function exists. So open, f of open being open, so to speak. What's that mean? So let's say f of u is v, x for u in the topology of x. That's in the topology of, well, let's say f of x. So if we have f inverse of v, well, I think that's equal to u, right? I mean, only if f isn't, so if f, but f is injective here, so for the open set here, the inverse image of it, that's not what I'm trying to say either. Dang it. That's not what I'm trying to say. This is f inverse inverse, though, right? That's the point I should be making. Right, because the inverse image of the inverse image. I'm not going to talk any more about this. No good sentences can come out of my mouth about this theorem at this point. Now, so he immediately goes to the weirdness of this theorem as it relates to space-filling curves. So if you have, if you have f from the closed unit interval 0 to 1, right, to, I don't know, the plane. Well, not the plane, but let's say the no, the plane would be fine. Right, but certainly, yeah, any Euclidean space, fine. But certainly R2 is Hausdorff. And so what this says, if your function is continuous on the closed interval, and if it's a one-to-one function, right? If it's injective, if it's continuous, and it's one-to-one, then it's a homeomorphism of f onto its image. The thing is, as he shows you in exercise 11, you can do stuff like this, as was pointed out by Hilbert. Yeah, you can actually build a surjection onto the unit square using this so-called space-filling curve. Would not be in, yeah, well, this, I think 11, it is, I want to say it's surjective onto the unit square. Anyway, I find these things to be somewhat vexing. One of the many sort of malevolent examples that was brought to us by Peano and these late 19th century troublemakers, right? threw into disarray many of the, I mean, you'd like to think that a path is one-dimensional. And so the idea that you can actually fill out the unit square somehow with a path, and I think adding insult to injury, the domain is 0 to 1. Maybe if the domain was all the reals, I could kind of like not be so annoyed, but I don't know. The real line and the real plane, are they homeomorphic? Yeah, I
You can make a bijection. I don't know if it's units though, is it?
there's the rub. What do we mean by continuous? Are we talking about continuous in the metric sense? Or are we talking about a different kind of continuity? We must be talking about a different notion of continuity, otherwise it doesn't, I don't know, I don't. All right, we'll talk about space filling curves another day. How about that? Okay, I mean, but King is right. This is one of the, but you know, something I have not proved in here, but can be proved. Rm is not homeomorphic to Rn for n not equal to m, and not at least not with respect to the usual Euclidean topology for sure. Now, maybe that's a question I don't know the answer to. Do there exist exotic topologies on Rn or Rm as point sets that make Rn and Rm of different vector space dimension homeomorphic? Is it possible to give some sort of weirdo topology to Rn such that, I mean, is there some weird topology on R5 that makes it homeomorphic to R2 with another equally weird topology? Or let R2 keep the Euclidean topology and just let R5 get weird?
I'm wondering if I forget what the non-useful topology of this empty set and the whole set might work.
Yeah, now that I asked the question, my immediate thought is to like look at R5 as fibers in some sense, like just take three-dimensional copies and like think of them all together at once, like just kind of don't allow yourself to separate points in three of the dimensions, make the open sets really, really big so that you can really only separate two of the dimensions. Maybe then that would be isomorphic, an isomorphism from R3 to R5. I don't know. I know with respect to the usual Euclidean topology, though, for sure, these are not homeomorphic. They do have the same cardinality, though. So, right. Ah, yeah. Apparently discontinuous. But proving that a bijection from R3 to R5 is necessarily discontinuous with respect to the usual notions of topology is actually a pretty difficult problem that I don't think we currently have the technology to solve. That was one of the things I found particularly vexing about topology, was just how long it took in my course for us to prove that Rm and Rn were not homeomorphic. That really bugged me as a student. Like, why is this so hard to prove? But it actually is somewhat involved. So the next section up is a relatively short section, and I'll just tell you what it says. It talks about locally compact. What does locally compact mean? So for each P in X, there exists open W containing P. such that the closure of W is compact. So any compact space is locally compact, and any non-empty subset of Rn is locally compact. Any discrete space, locally compact. So here's the theorem. If you have a locally compact Hausdorff space X, X, locally compact Hausdorff, and Y equals to X union one other point, let's call it infinity, then there exists unique topology on Y such that Y is compact Hausdorff. And the relative topology for X coincides with the original. It coincides with X's native topology. So what this theorem says is that if you have a locally compact space, you can convert it into a compact space by just adjoining one point. This is the so-called one-point compactification of the space. There's something that seems at odds with this theorem and what he writes. He says, more generally, a compact space Y is called a compactification of X if X is homeomorphic to a dense subspace of Y. Oh, there can be many compactifications of a space X. Okay, I got it. So the closed interval 0 to 1 is this is the compactification of the open interval 0 to 1, but the circle, all right, also a compactification. Which one is the one-point compactification? The circle, right? Because what it's saying is it's just gluing a point on an infinity, quote-unquote infinity. It's not really, I mean, you're just gluing the one, you're identifying the endpoints which you don't have as that extra point, thus making it compact. And these are not the same, these are topologically distinct. Anyway, that is something we can do, the one-point compactification. So we already saw, I mean, the that stereographic projection thing I showed last class, that is essentially the quantitative side of the one-point compact. That is an example of a one-point compact. The one-point compactification of the plane is the Poincare sphere like that, with the North Pole playing the role of the infinity. But something like that. Anyway, I'm sorry I could not connect with connection today. Apparently the connection lecture will be disconnected from the compactness lecture, but in some sense that seems appropriate, so you'll forgive me. I'll stop making puns now, let you go about your business. I'm sure your head hurts as much as mine does at this point.